video, I am going to explain the voltage and current relationships in balanced three-phase star-connected load. For this, let us consider a balanced three-phase star-connected load which is supplied with a balanced three-phase supply. Here, RYB are the supply terminals and these RYB are the load terminals. The wires which are connecting the supply terminals to the load terminals are called as supply lines or simply lines. So, the currents flowing in these three lines are called as line currents. They are denoted by symbol IL. The current in the first line is IR, current in the second line is IY and current in the third line is IB. The directions of these currents which are shown in this diagram are representing the assumed positive directions of current flow. The voltage across any two supply lines is called as line voltage and is denoted by symbol VL. The voltage across lines R and Y is VRY. The voltage across lines Y and B is VYB and the voltage across lines B and R is VBR. All these three are line voltages. Here, these are the three branches of the load. These three branches, they are connected in star. The currents flowing in these three branches, they are representing the phase currents, as these branches are called as three phases of the load. So, the first phase current is IPH1, the second phase current is IPH2 and the third phase current is IPH3. The voltage across every phase is called as phase voltage and is represented by symbol VPH. The voltage across the first phase is VPH1, across the second it is VPH2 and across the third is VPH3. These three are phase voltages. Here we have to derive the relation between line current and phase current, also between line voltage and phase voltage. Let us discuss about the relation between currents first. If we observe the current which is starting from R terminal of supply, that is line current IL, it is coming to the load terminal and entering the first phase of the load. So, the line current IR is same as the phase current IPH1. Similarly, line current IY is entering the second phase of the load. So, line current IY is equal to IPH2. Similarly, the third line current IB is equal to line current IPH3. So, IB is equal to IPH3. In general, we can say that the line current IL is equal to the phase current IPH. IL is equal to IPH. Now, let us derive the relation between line voltage and phase voltage. For this, we will consider the first line voltage VRY. VRY is the voltage across the lines R and Y. If we trace the path, we can see that this voltage is same as the voltage across terminals R and Y for the load. So, VRY is the voltage, it is the difference between voltages VPH1 and VPH2. So, we can write the relation as VRY bar is equal to VPH1 bar minus VPH2 bar. This can also be written as VPH1 bar plus minus of VPH2 bar. This addition we will do by using the phasor diagram. So, let us draw the phasor diagram. Here in this phasor diagram, we have considered VPH1 as the reference phasor. We know that the VPH2 phasor is lagging behind VPH1 by 120 degrees and the difference between the phase difference between VPH2 and VPH3 is also 120 degrees. Now, we have to add VPH1 and minus of VPH2. So, for getting minus of VPH2, we will extend VPH2 backwards with equal magnitude. So, this is minus VPH2. Now, let us add these two phasors by using the method of parallelogram. So, let us complete this parallelogram. Here, the diagonal represents the line voltage VRY. We know that the angle between VPH1 and VPH3 is 120 degrees. When we extend VPH2 backwards, this divides this 120 degree angle in two equal parts. So this angle between VPH1 and minus VPH2 is 60 degrees, and the angle between VRY and VPH1 is 30 degrees. Here VRY is the line voltage. We have to find out the relation between this line voltage and the phase voltage. So for this, let us drop a perpendicular from the tip of VPH1 on VRY. It divides this VRY in two equal parts. This is VPH1. So this distance is VPH1 cos 30 degrees. So the total distance of VRY, the total length of VRY is equal to 2 times VPH1 cos 30. So VRY is equal to 2 times VPH1 cos 30 degrees. Here we are considering the magnitude of VRY. So this is equal to two times VPH1 into root 3 by 2. This 2 will get cancelled, and we will get the equation for VRY as root 3 times VPH1. That is, the magnitude of VRY is equal to root 3 times magnitude of VPH1. VRY is nothing but the line voltage VL. So we say that in general VL is equal to root 3 times VPH. The general equation is VL is equal to root 3 times VPH. As we got the line voltage VRY by drawing a parallelogram, we can also get the second line voltage VYB by drawing second parallelogram with sides VPH2 and minus VPH3. Also, we get the third line voltage VBR by completing the parallelogram with sides VPH3 and minus VPH1. Now let us draw the phase currents in this phasor diagram. The first phase current is IPH1. This IPH1 is at an angle of 5 degrees with respect to VPH1. So this IPH1 needs to be drawn near VPH1 at an angle of phi, either lagging behind VPH1 or leading VPH1, depending upon whether the load is having lagging power factor or leading power factor. Similarly, if we assume that the load is having lagging power factor, IPH2 can be drawn lagging behind VPH2 by an angle phi. Similarly, IPH3 will be drawn lagging behind VPH3 by an angle phi.